Do you know there are some rarely occurring cancers that we can inherit from our parents through mutated genes? For instance, 1 in every 10 breast cancers is due to a strong family history. If we can identify such cancers early from a family history, we can potentially save lives. In this paper, we propose an unsupervised graph-based entity resolution application for accurate and efficient family pedigree search, which in turn will help early identification of genetically inherited cancers and other diseases. This research was conducted by me, that is Nishadi Kirialla, Charini Nanayakara, and Professor Peter Christen from the Australian National University, Chris Dibben, Lee Williamson, and Ely Garrett from University of Edinburgh, and Claire Manson from Public Health Scotland. This research was partially supported by ESRC grants, Digitising Scotland, and Administrative Data Research Centre, Scotland. Let's have a look at our application first. The Genetics Genealogy team of Public Health Scotland provides comprehensive family history research for patients with a potential familial cancer. The management of risk is dependent on the quality of the obtained family history information. The team explores birth, death, and marriage certificates held by National Records of Scotland since 1855, with the goal of building family pedigrees for patients. The current process of generating these family pedigrees is manual. This is a time-consuming and labor-intensive process. To automate this process, we propose SNAPS, Scotland Family Pedigree Search, which can generate family pedigrees for individuals from search queries. This is the architecture diagram of SNAPS. It has two main components, offline component and online component. In the offline component, we have the birth, death, and marriage certificates. We apply graph-based entity resolution techniques on those certificates and link records to obtain a merged dependency graph. Then using this graph, we generate pedigree graphs. Additionally, we generate indexes to be used for querying. Then, in the online component, a user first searches query values, for which we return ranked query results. As the user obtains a ranked list of matched records from the query processing and ranking step, they can select to explore one of the listed entities. When the user selects an entity from the query results, SNAPS extracts the corresponding family pedigree generated in the offline component. Additionally, there is an optional component in SNAPS that enables to anonymize a graph for educational and training purposes. In our application, we determine the risk of inherited genetic conditions of real-world personal data. If these are exposed to the public, these may reveal sensitive personal details and can pose a threat to the privacy of individuals. Therefore, we added this optional component to SNAPS, which can anonymize private personal data using publicly available data. The core of SNAPS is the unsupervised graph-based entity resolution step that links records appearing on birth, death, and marriage certificates. We first generate a dependency graph and bootstrap it. Then, we merge the nodes iteratively and generate the entity graph. In this step, we address the major challenges encountered in resolving person data. The first is attribute value changes over time. For example, women change their surnames after the marriage. Similarly, people move around and address values change. How are we going to link records when such attribute values are changing? The second is different relationships encountered at different points in time. For example, a baby in her birth certificate has relationships of mother and father. But when she becomes a mother herself, the birth certificate has completely different set of relationships, namely her baby and spouse. Then, the ambiguity of attribute values makes it harder to find the records belonging to the same entity. Next is the partial mesh groups. For example, when we want to link parents of siblings, we have to make sure we only link the parents, but not the siblings, because siblings represent two different entities. Final challenge is the likely wrong links that we encounter during the linking process. A detailed description of how these challenges are overcome in SNAPS is available in the paper. Now let's move on to a demonstration of SNAPS. We have hosted a prototype of SNAPS at dmm.anu.edu.au/snaps. You need to log in to access the private dataset. However, if you log in as a guest, you can access the anonymized dataset which is publicly available. Let me log in as a guest using the passcode guest. Let me try it again. The home page provides an overview of the tool. Now let's see how to search a query using SNAPS and find the corresponding family pedigree. For that, you have to first navigate to the Data Entry tab. In this tab, you can enter the data for querying. Here, we can specify where to search a particular query string, in birth certificates or death certificates. Then we have two mandatory fields, forename and surname, followed by gender, year range, and parish. In year range, we can select the period of time in which we need to search the query. And in parish or district field, we can filter the search results for a particular parish. For example, let's search for a person named Douglas MacDonald in the birth certificates. For that, I'm going to select birth and type forename as Douglas and the surname as MacDonald. I'm going to check male, and for the year range, I'm going to keep the default year range itself, and parish, I will keep it empty. And now I'm going to submit this. This will take us to the Query Results tab, which shows the query input and the results retrieved from SNAPS. It shows forename, surname, gender, event year, parish, and match percentage. It is important to note that these retrieved results are ranked based on the match percentage. Let's explore the family pedigree of the best match, Doyd McDougall. Exploring takes you to the Family Pedigree tab, which shows a textual pedigree for the selected entity. Interestingly, we can see three generations. The first is of the selected entity, Doyd McDougall, then his parents, and then their parents. For a clear view, let's generate the pedigree graph. In this graph, the blue color boxes show males, whereas the pink color boxes show females. Doyd McDougall has been born in 1868 in Portree, and we can see his mother and father. Looking at the father's entity, we can see that we have already been linked the father's death record. Then in the next layer, we can see Doyd's grandparents. Similarly, we can go back to the Query Results tab again and explore another entity. Now let me select Doyd Medgar from Snysort. Again, we can see three different generations. Let's generate the pedigree graph. We can see the details of Doyd Medgar, his parents, and his grandparents. Now, let's go back to the Data Entry tab and search the same query in the death certificates. I'm selecting death and submit. This will return matches to Douglas MacDonald from the death certificates. Let's explore Doyd McDougall and generate pedigree graph. For this particular entity, we can see we have only found two different generations. If you are interested, you are welcome to explore our prototype at dmm.anu.edu.au/snaps. That was a quick demonstration of our snaps tool. This is the end of my presentation. Thank you for listening.